Assalamu alaikum. Today I will tell you about my OS assignment. I have covered here two main topics of OS. First one is challenge was synchronization and performance in concurrent system. First, I will show comprehensive analysis of multi-threading performance improvements and user kernel mode transition. I will demonstrate a concurrent system that highlights the challenges of synchronization across user and kernel boundaries. Here is the part 1 solution. CPU bound task analysis, then running single-threaded CPU task and execution time throughput, and I will tell you about the result, set size and page fault count. As you know that task 1 was related to multi-threading and mode transition. Let me start with task 1. System measures 4 key performance metrics. First of all, I will compile my CP part 1, and then we will run the part 1. You can see that time execution, throughput, and result, working size, set size, and page fault count. And the program performs two main tasks: CPU bound task comparing single-threaded and versus multi-threaded execution, and I/O task bound and system call analysis, user kernel mode switching transitions. In our result, we can see that multi-threading provides significant performance improvements. The single-threaded execution took about 1 second for 200 million operations per second, while a multi-threaded execution achieved the same work in less time. For I/O operations, each small write operation triggers a small call forcing user to kernel mode over tasks, tracks page fault counts before and after operations as to estimate the number of system calls made. The performance difference is efficient, and CPU bound operations throughput 47 plus million elements per second as compared to the I operations 42,000 operations per second, demonstrating how system call reduce significant overhead. Now let's move towards part 2. First of all, I will tell you about the task 2, the concurrent system and synchronization. And now the task 2, the concurrent system, demonstrates the synchronization challenges across the user and kernel boundaries. And the key findings are remarkable. When we use kernel mutex, which require user to kernel mode transitions for each lock operation, our throughput is approximately. Let's run and tell you see that difference. You can see. Now I will run the part 2 is compiling our part 2, and then let's run part 2 transition mode overhead test. The for scalability, we tested 1 to 16 threads. You can see that thread 1 is executing, and 4 threads with kernel matrix, and it takes 1744,958 microseconds. Total kernel time is approximately 331.5 milliseconds. Final counter and total operations are 2 lakh. And this shows significant cost of mode transitions. Each time a thread needs to enter kernel mode to acquire a lock. There's a context switch overhead, privilege level changes, and security check. And that adds to execution. For scalability, we tested from 1 to 16 threads. You can see that 8 threads are high contention. It's testing throughput. And as this demonstrates that throughput in non-contention scenarios, low contention throughput is 15129 operations per second. 8 threads it took time 669 megasecond and throughput 118 operations per second. Scalability testing increasing thread counts. Thread 1 took time 752 millisecond megasecond and throughput is 31806 operations per second. Similarly for you, you will see that throughput and threads and time. We tested from 1 to 8 threads. Initially, adding threads improved performance, but after a certain point, the synchronization overhead begins to demonstrate, and we see diminishing returns. This demonstrates uh, Amdahl's law in practice. The sequential parts of our program limit the parallel speedup we can achieve. Now, as the program is running, uh, more transitions and the kernel mutex is around 21,112 throughput operations per second, and relative performance versus kernel mutex is slowed. You can see that 12 threads time is increasing and throughput is 13,704 operations per second. And the kernel mutex is around 296 times slower than atomic operations and 55 times slower than user critical sections. The overwhelming support the presentations called findings. The user to kernel mode transition is primary source of performance overhead is in simulation, scalability and Amdahl's laws. The scalability tester, which likely uses the expensive kernel mutex, demonstrate performance degradation as contention increases, confirming the presentation's reference to Adam's laws. बेसलाइन में जो था एक थ्रेड पे तो बेसलाइन थी दो थ्रेड्स पे ना लार्जेस्ट ड्रॉप हुआ था परफॉर्मेंस का वो 42% ऑलमोस्ट हुआ था ड्रॉप फिर फोर्थ पे तकरीबन ये हुआ है 24,024 में और इसमें ना 49.6% हुआ है उसके बाद ना 16 थ्रेड्स पे ना ऑलमोस्ट हुआ है ये टाइम के हिसाब से थ्रूपुट्स जो है ना वो 22 2% ऑलमोस्ट हुआ है 11840 तो 52% लोएस्ट पॉइंट हुआ है कंक्लूजन ये है कि ना परफॉर्मेंस immediately drop by 40% when moving from 1 to 2 threads as more threads are added the throughput continues and throughput continues and you can see that critical section kernel vertex and atomic operations और क्या है तो इसे हमें ना ये होता है कंक्लूड होता है कि ना more threads are added the throughput continues to decrease slowly in the diminishing returns an ultimate drop in performance compared to the single-threaded case. Clearly show that the synchronization overhead the sequential part of the execution demonstrates limiting the parallel speed up. You can see this code, access this code on my GitHub, Sohaib 28, and I hope you understood my code. I have made scalability test and comparison sync mode functions, and this is the end of the code. Thank you so much.